Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 6, and this problem asks us to determine the structure of a compound with the molecular formula of C10H14O2, and that shows a strong IR absorption between 3150 and 2850 per centimeter, and also gives the proton NMR, the HNMR spectrum of a triplet at 1.4, a quartet at 4.0, and a singlet at 6.8, corresponding to 6, 4, and 4 protons. So how do we go about solving a problem like this? Well, let's see what the information we have. So we have this molecular formula, and we have this IR spectra. So right away, we can look at our IR table sheet, and you can determine that this value here, these values, can correspond to an sp2 and sp3 hybridized carbon-hydrogen bond. Not only that, we have the formula of C10H14O2. And on top of that, we know that our product or our compound is going to have a total of these splitting patterns. So let's see what these splitting patterns are. Well, we have a triplet that has 6 hydrogens. So that means that these 6 hydrogens are neighboring 2 hydrogens, so the n+1 rule. These 4 hydrogens are neighboring 3. And a single hydrogen or 4 hydrogens are not being split by anything, actually. So let's see how we can determine this. So in order to determine something like this, what we need to do is we need to understand the formula of aromatic rings, and they typically have the formula of, for example, C6H6, or that would equal to CnHn. And this formula right here is C6H6. Well, that gives you a benzene ring. So we have 6 carbons. Then we have 6 protons as well. So if we use that similar formula, so if we just assume that there's going to be a benzene ring in here, and we know that there's going to be some sort of benzene ring because of this hybridization that we have here in the IR spectra, we see that we consume 6 hydrogens and 6 carbons. Not only that, well, it kind of seems like there's some sort of internal plane of symmetry in this molecule. And why is that? Well, 4 hydrogens are neighboring 3, and 6 hydrogens are neighboring 2. Well, this could be equivalent of saying that we have 2 terminal methyl groups, which is composed of 3 hydrogens each. And now, because these 3 hydrogens on each carbon are equivalent, the total neighboring, so if we have another carbon here, well, and if their neighbors are equivalent, if these are the same type of protons, then these 6 hydrogens would have a neighbor of 2. So then that would give us a triplet. And the same goes for this quartet. So now the red hydrogens, there's just 4 hydrogens in total. These are neighboring 3 hydrogens. So 3 plus 1 equals that quartet. So it seems like there's going to be some sort of internal plane of its symmetry. And the most important thing here is that the 4 hydrogens off this benzene ring all act as a singlet. So that means that these are all one type of proton. And the only way that we can get that is, well, if there's some sort of internal plane of symmetry. So we know that we have a carbon-carbon-carbon-carbon on 2 sides of the molecule. But we also have 2 oxygens. So let's add those oxygens first. So then after those oxygens, we can add the CH2, CH3, so then they can split each other. Then we get a molecule that looks like this. So now let's confirm what we've done here. So we have 2 terminal methyl groups, and obviously right off the bat we see an internal plane of symmetry. So we have 2 terminal methyl groups, and they have 3 protons each, so that's a total of 6 hydrogens, and these 6 hydrogens are neighboring 2 hydrogens here, so we have a 2 plus 1 equals 3, so these 6 hydrogens would show as a triplet. Now these 2 hydrogens here are the same as the 2 hydrogens on top because of that internal plane of symmetry. So we have 4 hydrogens, which are neighboring 3 hydrogens in this terminal methyl group, so we have a neighboring of 3, so 3 plus 1 equals 4, quartet. That's what we see in the HNMR. And now these 4 hydrogens in our aromatic ring, well, they all act as the same chemically distinct proton type. There's nothing unique about either of these or neither of these hydrogens. So they would just act as a singlet, and they would equal to your 4 protons.